I always forget to turn the microphone on. All right. Yeah. Okay. So, Beer's Law. You're going to be doing spectroscopy this time around. You're measuring light. Spectrum, light, scope is a device for measuring light. So, spectroscope. Spectroscopy is the act of doing the spectrum reading. So, you pass light through materials, and you can use the way the light interacts with the material to better understand the material or light. We can see this with prisms. Light passes through the prism, it refracts, and it breaks apart into a rainbow because different colors of light interact with the glass slightly differently. Now, in this kind of spectroscopy, we pass it through a solution. You know, substance A dissolved in substance B. It's usually some chemical dissolved in water for the work we're doing. And this is governed by Beer's Law, which is hard to read here on this screen, so I'm going to write it out on my page here. Okay, good, it's upright. So, A equals epsilon L C. A is the absorbance, okay, how much the light is absorbed in the solution. Epsilon, that is a physical property of the substance being measured. So it's, you know, how absorptive it is for that particular frequency of light. L, how far light goes. Basically, how long of a path does the light have to take to get through the thing. And C is the concentration. So epsilon is just a property of the substance, and that will change for the different substances and, you know, different wavelengths of light. L, how far the light passes through the substance. Think about it. If the light passes through more of the solution, then it's going to interact more with the substance you're analyzing, and thus it will get absorbed more. And likewise, concentration. The more concentrated your solution, the more substance there is for the light to interact with. You can see both of these, and they're fairly straightforward. L, water looks clear in just a glass, but a swimming pool looks blue. The ocean looks blue. This is because the light is passing through a lot more water. Water absorbs red light very, very small amount. So it takes a lot of water before it's absorbed enough red that the blue starts to overtake it. And you can see concentration as well. You take a very concentrated thing that has a lot of color, you dilute it down, then that color will go away more and more and more. Or conversely, you know, you add more and more, say, food coloring to water, it'll turn a darker and darker color. So this relationship holds true at low concentrations. Because at higher concentrations, the solute particles, the stuff you're looking at, they can start to interact with one another. The most basic way of thinking about it is like they cast shadows. But it's actually more complicated than that. They can pass energy from... Anyway, the point is, this is true for dilute solutions, not really highly concentrated solutions. And the great thing about it is that it's straightforwardly linear. If you keep epsilon constant by only looking at the one substance, and you keep L sub constant by setting it up so that you're always passing it through the same amount of liquid, then you just get a nice straight line where you graph absorbance on one thing, on the y-axis you graph concentration on the x-axis, and when you do that you can get, you know, a nice straight line at low concentrations, where the slope of that line is epsilon L. So one thing you can use spectroscopy for is to measure concentration. Another thing you can use it for is, if you know the concentration, you can use it to measure epsilon. Okay? So you can actually measure a physical property of the material. So one of the things you have to learn for this lab is concentration. And that means how you prepare solutions. Now, we measure concentration using molarity. So molarity, big M, is measured in moles of solute per liter of solution. Okay? So remember, the solute is the thing being dissolved, the solvent is the thing doing the dissolving, and the solution is the combination of the two. So molarity is moles of solute per liter of solution. This is an important thing to note because it means that you have to get your final volume with the solute already in there. If you were to say, take a liter of water and throw some salt in there, you are going to have more than a liter of salt water because the salt has volume. Now, it's a very, very low volume, especially once it's dissolved, but it's still there. It still makes a difference. So the way you prepare a solution is you throw a little bit of water in there, step one. Step two is you throw your solid in there. So after you do that, you throw in your solid. You have enough water in there that you can dissolve the solid. And then step three, you add water to get it up to the volume you need. Okay? Because with the solid already dissolved in there, you keep adding water, then you have the volume of your solution as a whole. So if you wanted to make 1 liter of a solution, you'd have your solid, you dissolve it in a small amount of water, swirl it around, and then you would add water until you had 1 liter. Okay? You wouldn't start with a liter, you end at a liter. All right. Now, the other thing is that we're talking about moles of solute. Okay? So this is not a measurement that uses mass. It's a measurement that uses moles. So if you wanted to produce, say, 1 liter of 0.500 NaCl solution, how much salt would you need? What mass of salt? Well, 0.500 molar means 0.500 moles of NaCl per 1 liter of solution. So in order to make 1 liter of this 0.5 molar solution, we need half a mole, because it's 0.5 moles per liter. And 0.5 moles of NaCl, well, sodium chloride has a molar mass of 58.44 grams per mole. So half a mole is going to be 29.22 grams. So in order to make 1 liter, 1 liter of a 0.5 molar solution, we need half a mole, or 29.22 grams. So we take a little more than 22 grams, and we chuck it in some water, swirl it around till it's dissolved, and then we add more water until we get up to a liter. Now, making a liter is kind of excessive. That's a lot. Okay, a liter of water, well, that's half of a 2-liter jug of soda, and that's way more than you're likely to need in a lab. We typically work with smaller amounts. So you might instead, and also 0.5 molar is fairly concentrated, you might instead make 250 milliliters of, say, 0.500 molar. That capital M is what we use to represent molarity. Say, sodium chloride. So we look at our thing, okay, how much sodium chloride do we need for this? Well, that's still 0.500 moles of NaCl per liter of solution. We want, liter and milliliter. That's a disconnect. Well, this is just one of those unfortunate things. We typically work in mils because those are, of a convenient size for, small manipulations. But molarity works in liters because that's convenient for large manipulations. And we have to be able to go back and forth between these two because we usually make a lot of solution when we're talking about routine work. Okay, so industrial labs, things like that, will have large stocks of some solutions. So molarity is standard moles per liter. But then, for hands-on solutions, for the individual bits and bobs we do, we'll work with mils because that's what, is better for that. So remember, converting from milliliters to liters is easy. You divide by 1,000. There are 1,000 milliliters in 1 liter. So 250 mils is 0.25 liters. Okay. So 0.2500 liters of solution. So 0.5 moles per liter, we have a quarter liter total, means that we need 0.125 moles of our NaCl. So now with that information in hand, how many grams of sodium chloride would we dissolve in 250 mils? Well, it's just going to be 1/4 what we had before, because we have 1/4 the total volume, but still 0.125 moles of sodium chloride multiplied by 58.44 grams per mole gets us 7.31 grams. Always double check my math. If I don't bring up a calculator, then I'm doing it in my head, which means I could be screwing up. In this case, I just divided by 8. And I think the way it rounds this one. Anyway. So once again, you dissolve 7.31 grams of our sodium chloride, table salt, and a little bit of water, and then we add volume until we get to 250 mils. Now, the glassware we use for this, you can see it in the background here, over on the right. That's known as a volumetric flask. Okay. You can see it even more clearly right here. Okay, a volumetric flask is a really, really great piece of glassware that it can only measure one volume of liquid. And then it can't even deliver that volume accurately. They are typically used for making stock solutions, for making something with a very precise volume. The shape is really well suited to making solutions because you can swirl the stuff around in the bottom and it won't climb out the sides and come out the top. And you can't really see it here. It's barely visible. They have a line marking on the neck that tells you that when you get to that volume, or when you get the meniscus to that line, then you have exactly the volume of that particular flask. This one is a 500 milliliter volumetric flask. So that flask will measure precisely 500 mils, and only 500 mils, but it's really, really good at it. So that's how you would make a solution like that. For a 250 ml solution, you would use a 250 milliliter volumetric flask. For a 500 ml solution, a 500 ml flask. That's if you want, a really well characterized solution, and you usually do. So what you're going to do in this thing is, first you're going to make a stock solution, and then you're going to make dilutions from that. Okay. So what you'll be doing is you will be measuring a couple of things. Okay, so first you're going to use, just call it solution A, just some quantity to find out, to find the good wavelength. Okay. See, a material will absorb different wavelengths of light, better or worse, more or less. Okay, you measure absorption against wavelength, and you'll get something like this, where it might measure really strongly at one color of light or very, very weakly at another color. You would not have a device that would create a really good spectrogram like this, or spectrograph, excuse me. So instead, what you'll do is you'll measure at a couple of different wavelengths to try and find a good wavelength where you get higher absorption. So you might measure, say, 5 wavelengths, 400, 500, 600, 700, something like that, blue, green, yellow, red. And you might find, that absorption here is 0.1, 0.5, 0.3, 0.4. It won't be linear at all. These graphs usually go all over the place. because it's just how does light interact with the compound, and that's going to vary based on what sort of compound you're looking at. And so you would see here, in this random example I've made up, that if you want to measure how the thing responds to light so that you can measure concentrations, you want to use this color of light, because that's where it responds most strongly. You want good, strong absorbance so that you get good, strong signals, even at very low concentrations. So that's the first thing you do, is you try and find the best wavelength available from a limited set of options. The second thing you do is you now look at creating a graph for Beer's law. Okay? So you'll be holding the wavelength of light constant for the second part, and instead you'll be varying the concentration so that you can get this slope and basically get a measure of epsilon. So to that end, you'll need a bunch of different concentrations of your solutions. So what you'll do is you'll make stock. And you'll make a big, high concentration, high volume. Okay? And then from this stock solution, you'll make a bunch of dilutions. You'll make a number of things with lower concentrations and also lower volumes, because you're just using them to measure epsilon. You don't need a whole lot of them. And to do that, what you use is this guy here. Okay. You see, when you dilute a solution, okay, all you're doing is adding water. Okay, so to increase the volume. And when you increase the volume, the amount of the solute is staying the same. Okay? So remember molarity, moles of solute per liter of solution. So the solute stays the same, the liters of solution is what's changing. And molarity times volume is equal to moles. So the moles of solution stays the same. So the molarity, the concentration, multiplied by the volume at the beginning of your dilution is going to be the same as the molarity times the volume at the end of your dilution. The volume will increase, so the concentration will decrease. Okay. So if you start with, say, 50 milliliters and you add 50 milliliters of water, you get it up to 100 milliliters. You've doubled the volume. The concentration will be cut in half. You go from 1 to 10, the concentration will go down by a factor of 10. Okay? You go from 1 to 100, it'll go down by a factor of 100. So dilutions let you start with a high concentration stock solution and then make a bunch of different diluted solutions. So that's what you're going to be doing. I don't recall off the top of my head the exact numbers, but I think you will be finishing at a total of 5 mils each time. So your total volume, or volume 2, will always be 5 mils. So let's say you're doing 4 dilutions. Actually, let's say 5. Okay. So your initial volume, V1, would be, for example, say 1, 2, 3, 4 milliliters. Okay. So 1 mil, 2 mils, 3 mils, and 4 mils. And the amount of water you're adding is obviously going to change each time. So add 4 mils, 3 mils, 2 mils, 1 mil. And because you're starting with different initial volumes, M1, you're going to end up with different initial or different final concentrations based on V2. So you'll know the initial concentration of your stock solution, and you'll know the initial volume, that's what you started with. You'll know your final volume, that's what you end with. So you'll be able to find your final concentration, M2. You just rearrange this and you get M2 equals M1 V1 over V2. So this one would go down by a factor of 5 because you're going from 1 to 5. This one would go down by a factor of 2.5 because you're going from 2 to 5. This one would go down by a factor of 5/3. This one would go down by a factor of 5/4. So you'd end up with a bunch of different concentrations. And so what that will do is that will give you multiple points to measure on this graph. Okay? You'll have, low concentration, higher, 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 and then that will get you the 4 points on the line. You'll be able to draw this great curve. Now, in an ideal world, this line should go through 0, because if you have 0 of your solution, you should get 0 absorbance. All right. So, well, in this case, you're not going to be doing it by hand. Actually, you'll be doing it on a simulation, but still. You'll first you'll choose the wavelength in order to get high absorbance, and then you will set a number of different concentrations, and then you will get your curves. Okay. Let's see. Oh, yes, you'll also have to calibrate. Because you want to make sure that you're not measuring your solvent. You want to ignore your solvent. Your solvent may also absorb weakly or strongly at the particular wavelength you've chosen. So you always start with what's known as a blank, or at least that's what I've always called it. That's like hitting the tare button on a scale. You don't want to measure the weight of the container that you're measuring your substance into. You just want to measure the weight of the substance. So you put the weigh paper or the weigh boat down, and you hit the 0/T button. You're doing the same thing with your blank. You have just the solvent by itself with no solute in it, and you measure the absorbance, and then you can calibrate for that, so that you automatically ignore that. You got to remember to keep that in account. All right. That looks to be everything. I may have forgotten something. These things are always complicated, and I don't want to sit down and watch through 3 hours of video in order to get these things. So that's Beer's law. That's how you do various solutions and concentrations. Remember that when you're doing your Beer's law math, A equals epsilon LC. Okay, so C is the thing you control. A is the thing you measure. The slope of your line is going to be epsilon L. So technically, in order to get epsilon, the actual physical property, you're going to have to take L into account. How much, what length of solution is your whatchamacallit passing through? That only a slight complication should be easy enough to eliminate if they actually ask you to do that. They might just stop at asking you for the slope. Also, be careful about your concentrations, because they might not be evenly spaced, depending on how they ask you to set these things up. Now, the other thing is, despite the way I've drawn it, these guys, each one draws its initial thing from the stock solution. They're not being diluted successively. So you're not making a concentration of 1 and then diluting that to make 2, diluting that to make 3, diluting that. No, you're making them all. You're making all of them from your stock solution. And also be aware that M1V1 equals M2V2. This only works when you are diluting a particular solution. This will have different ways of working if you're doing, say, titrations, and you're relating moles of one substance to moles of a different substance. So this is just for dilutions. Be careful about what your initial molarity and initial volume are, final molarity, final volume. Try and keep all those things totally clear. Okay. All right. Good luck with your lab. Remember, it is due by Sunday evening. I will see you around.